couple things before we get started, really. Don't forget the math in take place this Saturday, April 30th, from 10 a.m. to 5 p.m. here. By here, I mean in this building. We'll put up signs for where it's the appropriate place to go. Please take advantage of that. Also, I will have a review session for this class. Y'all know your exam schedule. Is there any time Wednesday? Wednesday's just probably the only day that I'm going to be able to work out. Was it probably in the evening sometime? Okay, so I'll look around and try to get something reasonable in the evening then, and I'll let you all know. Okay. So what we're going to do is we're going to use all this group theory stuff that we talked about and attempt to apply it to having your own kind of technique to solving the cube. I'm going to show you what I came up with, or I'm going to kind of guide you through it in a certain sense. But the power of this is you'll have the freedom to create your own moves and your own shortcuts and things like this. Now, before we get to go, and this is in your notes, I've got some pictures. I'm going to update your notes today, actually. But we need a map of the cube so that we can talk intelligently about it. And I call these pieces corners that have 3 colors on them, right? The ones that are obviously on the corners, and I number these by the letters in the alphabet between A and H. And then I call the pieces that are side pieces, I label them with numbers 1 through 12. They're the pieces that only have 2 colors on them. And I'm ignoring the centers for this purpose. There's one more thing that I have to do. And that map is getting a little bit too busy. I am going to define for each side piece and corner piece an orientation. So basically, notice that if you have a corner piece, there are 3 ways to orient it, right? Because you've got 3 sides and either one of them can be pointing up, right? So I am going to number, I'm going to go all zeros across the top here. The corner pieces, I'm going to orient it this way, 1, 2. And on the back side, 1. This one is going to be 1, 2. You can orient these either way you want, but you have to have a 0, 1, and 2 on every corner piece. And I tried to make this pattern so that we can see what I have here. So it follows this pattern. 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. And I am going to note that the side pieces only have 2 orientations, right? Because this piece is facing up and this part is facing up. And so this will make my life easier too. You orient this all zeros on the top. Yeah, it's all on that side. And hopefully you all pick up the pattern on this. So this is oriented all zeros on the top, all zeros on the bottom, and you got to kind of mix and match across the belt. Now, I can make this. Do y'all remember this trick I did when we were first talking about this? And I said, move this and then keep going, right? Anybody remember how many times it took to fix it? Yeah, it was like 105, wasn't it? Let's take a closer look at this. And in fact, I asked you a homework problem, I believe, last week, where I did something equivalent to that. Does anybody remember? I asked the question, turn this and this. Oh, it was the top and side, but it's the same thing. And I asked, how many times does it take for it to get back in geographically correct position? Anybody remember what the answer was on your homework? It was 35 to get it geographically correct. Let's see what we do. And I'm also going to introduce some notation. So I'm going to consider the following move, just this simple move. And it's something we've seen before, but I'm going to take this apart to show you how to kind of really dig into this. Well, before I do this, I'm going to talk about basic moves and notation. By the way, here's some Rubik's Cube proving facts. You all should be able to figure this out because this is like one of the counting problems before, but yes. Right? You have 12 factorial ways to input the side pieces, 8 factorial for the corners. Every corner has 3 ways you can orient it, and every side has 2 ways, right? This is the number of ways that you can assemble a Rubik's Cube if you imagine it was all pulled apart and you're putting it back together. Right? Number of arrangements on solved cube. About 112. That is to say, if I take this solved cube and I scramble it and I record everything that I could possibly do without pulling it apart with pliers or taking the stickers off, that's the number of arrangements that you get. Notice that it's 1/12 the above, right? The moral of the story is, if you ever take your cube apart, put it back together solved, because if you put it back together at random, there's only a 1 chance of 12 that you can solve it without pulling it apart again. Why is it 1/12? When we talk a little bit about this orientation in a moment, I'll explain this a little bit. By the way, this number is about this may not seem like a very impressive number to you all. In fact, how many of you have had a chemistry class at some point in your life? This is smaller than that Avogadro's number, right? So this might seem like a tame number, but just to give you some perspective on how big this number is, if you took, so I wrote it, I think the population of the United States has about 300 million people, and I guess it's a little more now. If you took a Rubik's Cube and gave a Rubik's Cube to 300 million people in a line, and said, go. And when you said go, every person starts scrambling their cube. And every person, all 300 million of them, get a different combination every second. Not only do they get a different combination, they get a different combination from what everybody else gets. And nobody, of the 300 million people, nobody repeats the combination. So all 300 million people are getting a new combination on the Rubik's Cube every second. And this is recorded in some large computer so you can count it up. If this line of people keeps collecting new combinations, all 300 million of them every second, and they do this 24 hours a day, day and night, for 40 years. At the end of that time, they will have amassed about 0.8% of the number of combinations. So this is a very large number. In fact, here's another frustrating thing about the Rubik's Cube. At any point on the Rubik's Cube, so I see you've got your scramble. I don't know how to do it because it's actually a hard problem. But if I call this one move, just a 90-degree turn on one side, we are less than or equal to 26 moves away from solving that cube. Right? But finding that short path is very difficult. Right? So, and in fact, you probably scrambled it more than 26 times since you played with it, correct? So don't ever say I never gave you anything. With a very high degree of probability, we are the only human beings to have ever lived on planet Earth to see the Rubik's Cube in this path. So, obviously, it's going to take a little brain power to solve this, right? So kind of guessing. Let me tell you a little bit about Rubik's Cube notation. So, I'm going to abbreviate my sides. I'm not going to use some of them because I can just turn the cube. So, R, right side. And here, when I say side, I don't mean the side piece. I mean actually the whole side. So when I use that notation, that means turn the right side clockwise 90 degrees, R prime, right side 90 degrees counterclockwise. And let's see, the other ones I'm going to use are down, front, and right. Front, left. Some, if you look at some cubes, they use up and back. Okay. So R means turn to right, clockwise 90 degrees. R prime means turn counterclockwise. Down means turn the bottom down. And how do you determine what clockwise is? Imagine you slide under it like you're working on a car. Down means turn it clockwise. Down prime means turn it counterclockwise. And the same applies to the front side, the left side, and up or back. But I'm just not going to use up or back. And don't confuse the D and the F with what I've labeled there. So hopefully it'll be clear for the context. These are moves, not pieces. So moving right counterclockwise and down counterclockwise is written R prime, D prime. Now, this really kind of makes me angry, and I thought and went back and forth about changing this for you, but if you look in any kind of literature, if you get interested in this stuff and read yourself, it is common when you read moves, what they mean is they do moves this way. So just like you're reading English. So this means I move the right counterclockwise and down counterclockwise. Unfortunately, when we do the computations to see what it does, we're going to have to use the permutation group notation. So we're going to have to put it in the other order, right? Just like function composition. So what I want to do is I want to look at what right prime down prime does. All right, right prime down prime. I want to take that apart and see what I can do. Well, right prime and down prime, all these moves, basically, operate on two things. It does subtract to the corners, and it does subtract to the side pieces, right? So let's look at the corners first. This is going to be my right prime and my down prime because we do a function composition. Yes.
Are we assuming, for the sake of this example, that this arrangement could be any arbitrary, does it have to be already solved from this arrangement of labels, or does it not matter? It's from
I'm going to start from solve cube, but it doesn't matter, right? I mean, in any configuration on the cube, we can do this way. But what we're going to do is see what the composition does. So let's look at the corners. Let's do right prime first. So what I'm doing is I'm rotating my right side counterclockwise. So B goes where? It goes to C, so okay, that's the way it goes. And C goes to what? G to F. And the down, let's see, if I get up under there like I'm working on the car, counterclockwise, C goes where? Agreed. Which goes to, and then, everybody cool with that? Now, I'm going to go a little bit further into this, right? Because here's what it does, right? Now, we've seen this before, and this is an outcome. So I'm just going to write outcome sort of naked like this. We'll see alphabetically. I come to B first. B goes to where? Right. Good. And D goes to A, which goes to, how about G? F. And F. B, right? Did I cover all the letters? I covered everything except C. Where does C go? It dances. It goes to G and then back to C. And conveniently, we'll do the sides over here. Might as well strike while the iron's hot. Do the R prime here, and on the sides, we'll see counterclockwise 2 goes to 5 to 10 to 6. Everybody okay with that? And down, 9 goes to 12, 11, 10. Now, if we go through this, let's pick this up with 2, it goes to 5, and then it's done. 5 goes to 10, and then to 9, 9 goes to 12, 12 goes to 11, 11 goes to 10, 10 goes to 6, and 6 goes to 2. That's okay. Everybody okay? So this is probably part of what you got on your homework, right? You say, okay, so we've got a permutation on the corners. It's just a single cycle in 5. So every 5, the corners are fixed, right? And on the sides, we've got a permutation of order 7. So every 7, the sides are fixed, right? And so for 35 here, so if we do this, so actually, just for fun, let's see what happens to C. C should be this corner right here, the old good old American red, white, and blue one, right? And when we do this, notice the C is still in its place. Now it's all twisted, right? 2, 3, 4, 5, 6, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 6, 7, 30, 1, 2, 3, 4, 5. And here, folks, we have solved cube. Now, I'm only half kidding, right? Because if you look at this cube, it is geographically solved, right? For example, look at our old friendly red, white, and blue piece. There it is, right where it belongs. It's just twisty. What goes here is yellow and red and blue, and there it is, and so forth. This is a geographically correct cube, but it doesn't look very pleasing to the eye because some of the stuff is twisted, right? Let's see how we can detect that. We're going to do orientations here. Now let's go back and see what these orientations do with the second one. Now, what I want to do, so you guys don't have to follow me with the way we do orientations here. The way I'm going to do orientations is in the first move, so I'm going to look at R prime. We go from B to C, right? To get, so there's more than just the move, there's the orientation. Look at B. The 0 on the B is on the top side, right? The way I orient. When I flip B to C, let's see, I'm going the wrong way. It's counterclockwise, right? When I go from B to C, where does that number 0 end up? In the place of the original, what number? 1. Notice how the 0 is in the 1's place. I call that a 1 orientation. How about C to G? Well, the orientation on the C block, the 0 is on the bottom. So when I flip it here, can you guys figure out? Let me finish this off here. Can you figure out where it goes? What's from back there? That's it. How about when C goes to, I'm sorry, when G goes to F? The zero piece for G, the 0 side for G is on the bottom. Where does that end up when I go this way? So I'm going counterclockwise. The 0 for G is on the bottom. Where does that end up when I spin it up here? Agreed. There's 1. And I bet that's a 2 without looking. By the way, let's check, shall we? The 0, 1 on F is on the top, and when I spin it, it ends up at the 2 place. So I got that right. Anybody know how I knew how to fill in 2 without doing this? This is kind of a good thing that kind of hints, helps you know that you've got this right. How many sides are there on the corner piece? There's 3. Your orientations must always come to a multiple of 3. And at this point, I had 4. I got to stick on a 0, 1, or 2, but I've got to make it add up to a multiple of 3. There's only one choice. Notice that this adds up to 6, which is a total of 0. How about the bottom? Can anybody tell me what the orientation of the bottoms are? Oh, I made this very convenient for myself. So when I turn the bottom counterclockwise, notice the 0 is on the bottom, and there's all zeros on the bottom, right? So when I turn that, this is a total 0 orientation, no matter how you do it. Everybody see why that's true? That was very convenient when we put zeros on the bottom. So let's see what the overall effect is, right? Okay, let's follow this more carefully. B goes to C, orientation 1, and then C is kicked on to D and it's not changed any, so it's a total orientation of 1. Everybody okay? Okay, let's see where D goes. No D over here, so D just goes over here, 0. There's no H here, H goes on to G, 0. G goes on to F. Well, let's see, what is G? G goes to F with orientation 1, and then on to C. Oh, I'm sorry. Totally freaked out there. G goes to F with orientation 1. And what happens? F goes to B, and what's the orientation there? What does this come to? What are you supposed to have to say? C goes to itself, it changes its orientation, which is exactly what it's on here. Remember our good old red, white, and blue C stay in the same place. Right? Let's check this. C goes to G of orientation 2, and then it doesn't change going back to C. So there you go. So now we have something a little better. Because, oh, well, let's check the sides here. Anybody tell me what the side orientations are? Two, 5, 6, 10. These are all 0. 9, 10, 11, 12 are all 0s on the bottom. How about that? These are all 0 orientations. Nothing happens here. Now with this more sophisticated look at the orientations, I can tell you what the order of this move is. Let's look at this a little bit closer. If I do this 7 times in a row, this is correct. Correct? What happens if I do this 5 times in a row? What happens if I do the corners 5 times? Every 5 times, what will happen is, where does B go? Well, if I do this 5 times, B goes to D, H, G, F, back to B. Agreed? But its orientation goes 1, still 1, still 1, 2, so we're up to 2, 4, which is the same thing as 1. That is correct, right? Every 3 is a 0, right? What happens to D? Well, let's see. D goes back to itself 5 times. Let's see what happens. Goes to H, no orientation. G, now we're up to 1. Now we're up to 3, back to 1. So D is a 1 as well. Hopefully you all see this pattern. When you run through the cycle, you'll always get orientation 1. And what happens to C? C just sits there and turns, right? It stays in the same place and turns, and it does the orientation 2 5 times. So it'll be oriented 10, and 3, that's the 1. By the way, look what happened. That adds up to 6. All your orientations put together. So if you do this 35 times, that's the same thing as doing this 7 times. Agreed? So this is 7, which is 1. predicts exactly what will happen if you do this 35 times. All your corners will be correct. See, they're all oriented correctly. In fact, every 7 times you get the corners correctly. However, your corners, and there should be 6 of them that are out of whack, right? And they're all turned the same way. These two, these two, these two are all out of whack. Question? Yes.
So numbering that shows for the orientations or like the way that you represent that wouldn't necessarily matter because no matter what.
What you need to have happen is on all the side pieces, you need a 0 and 1, right? And on the corner piece, you need a 0, 1, 2. And I did this for convenience, right? Because it works out nicely, but yeah, it doesn't matter how you do it. It should work out. As long as you follow those rules, that everything, every block is a 0, 1, every corner block is a 0, 1, 2, and every side is a 0, 1.
So you could write the script for that. Then.
Oh, what now?
Like you were to describe what that would be like 0, 1, 2 cycle.
So this basically the orientation tells. So for example, this one right here. Let's see, where's B? B is this block right here. It's the red, white, yellow block. What you've done is basically you have turned. What you've effectively done with this B1 here is you've taken this block and you have rotated it clockwise 1. And that's what that means. 1 turn clockwise. Right? If you do this another 35 times, you will find that these will all be turned twice clockwise or once counterclockwise. You do it another 35 times after that, it will be turned 3 times clockwise and everything will be fixed. Does that make sense?
Yes. But what would you like if you were to, like, I get that repeating cycles like a unit, but like, how would you refer to like structure that's defining the corners?
Oh, actually, if you want to talk about the group theory one, what happens is there are 2 groups. Well, there's several groups going on here. One of them is a permutation of corners. So it's like an S8. That affects the geography of the corners. There's another group that's an S12, permutations of sides. That affects the geography of the sides. And then there's a couple of other groups, and these groups are all linked together to make a big parent group of this. One group is 8 copies of the cyclic group of order 3. And that conforms to turning this, right? And there's a little caveat on that. And there's 12 copies of cyclic group order 2 that controls the orientation on that. And these are all they're kind of glued together. It's a complicated group. Other questions? I am going to get to the first piece of the puzzle. So suppose that I have a root here like this, and I've got like something to solve, right? So in theory, you all might be able to get this, where you've got like one level, right? The top level. Maybe it's a little iffy, right? But you can get it. Now, this is where it gets hard, right? Because the reason I wanted you to practice with this is because getting one level is, I don't want to trivialize it, it takes a little practice, but you got a lot of freedom, right? But now that you've got one side, you're almost afraid to make that omelet, right? Because, right, you got to break some eggs, and you don't want to mess up what you got. So what I need at this point to move forward is I've done this work here. I need to find some moves that leave this alone, but somehow yin yang with this stuff down here, so that maybe I can move things around and solve it. So let me give you the want us to analyze. So let's look at the following move here. So y'all probably want to get a pencil piece of paper to help me with this. Let's look at move. Let's do this. I'm going to write this in how you would do it notation. D prime, R prime, D R. E F E prime. Okay. So I'm going to put some temporary labels here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. This is 8 nodes. 4, 5, 6, 7. Okay. So remember to run this in reverse order. This is D prime, R prime, D, R, D, F, D prime. Okay, this looks like a lot to fill in. It's not so bad because we can do a lot of repetition. Okay, what's D prime on the corners? That's turning the bottom row counterclockwise, right? So that's C, D, H, G, right? Now, I want to fill in a bunch of stuff to make myself easier. D prime, there's another D prime here, C, D, H, D. And this also makes the D's easy to fill in. Why are the D's easy to fill in? It's just the opposite order. That's exactly right. G, H, D, C, and G, H, D, C. Now, let's do F and F prime. Okay, that's the front. The front clockwise is A, B, C, D. Okay. Counterclockwise, C, C, A. And let's do the right. The right counterclockwise is B, C, G, F. And counterclockwise is F, G, C. C. Okay, I'm not going to do the orientations on this one, please. Yeah. This oh, let me do this. Okay, so let's do the size as well. D prime. Let's see, counterclockwise, it's 9. Well, it's 12, 11, and 9. And it's 9, 10. Well, 11, 9. Okay, so what else we got? Front. What's front? Front clockwise is 1, 5, 9, 8.
12, 11, 10, 9, down clockwise.
12, 11. Maybe, let me think. No, clockwise should be 9, 10, 11, 12. Right? Because if you slide under it like you're working on a car, right? 9, 10, 11, 12 is clockwise. So 12, 11, 10, 9 is counterclockwise.
Oh, 11's in the back.
Yeah, 11's in the back.
Sorry, yeah.
Okay, so let's do the front. The front goes 1, 5, 9, 8 when I do it clockwise. So it's 8, 9, 5, 1 counterclockwise. And that just leaves me with the right prime. Right counterclockwise is 2, 5, 10, 6. And 6, 10, 5, 2. Okay. Again, we're not going to look at the orientations just yet. But maybe we won't look at the orientations. That's my, but let's see what we get. Well, let's start with the first thing I see. Where does A go? Somebody take a gander at that and tell me if you can tell me where A goes. Okay, good. How about B? So, how about C? Back to the cell. D. I hope this isn't the identity because I'm not seeing it bad, but we'll see. D goes to are you sure? Yeah. That's what I got. I think he goes to H. How about H? Where does that head up to? Yeah, I agree. How about G? Back to D. Okay, so what do we got left over of our letters? A, B, C. I'm missing an E, but there's never an E anywhere, right? So the E's left alone. So I can I'll write that there just to emphasize there was never an E in the first place. How about F? Agreed. Okay, let's take a look at the sides. Start with 1. Why not? Where does 1 go? Agreed. So the 2. Three. Well, there's no 3 in the first place, so that better go back to itself. I don't think there's 4 either. So that's got that licked. How about 5? How about 11? Agreed. 10 goes to. Right. How about 12? Yeah, that's right. I got that. About 9? Goes back to 5, doesn't it? So I'm still missing some numbers. Let's try 6. Back to the cell. And 7 and 8 are the last ones missing, but oh, there is no 7, so it goes back to itself. And 8 better go back to itself. I think that's the only one left. Let's see what happens. 8 goes to 1 and back to 8. How about that? So can somebody explain to me, okay, so now that we've done that, anybody tell me what the utility of this is? What does this move do once we do this? Effectively, what it does is on the sides, it leaves alone A, B, C, I don't care so much about C, E, and F. Right? So in other words, in particular, A, B, E, and F are left alone. This means my top row is going to be geographically correct. And what does it do? It takes D, where are you, D? D and H along the back, and G, and they do a little dance. All right? Moves these bottom pieces. The utility of this comes from the sides. What happens to the sides? 1, 2, 3, 4 are fixed. So again, my top row is looking in good shape. 6, 7, and 8 are all fixed too. So that it leaves alone the second, most of the second row, except for 5. And what does it do to 5? It kicks it down to where 11 is, right? And then the ones on the bottom, 9, 10, 11, 12, do a little dance, and 9 kicks back up into 5's place. So this allows me to take something in a position of 9 that is on the bottom row and push it back up into the middle. So for example, okay, so for example, if I hold the cube this way, see this piece right here? It's orange and yellow. I want it to go up to here. I want 9 to go to 5, right? And that's what this permutation does. It takes 9 to 5. I don't care so much about the rest. I want this guy to slide up here and everybody else to be left. Well, I don't care who's dancing around here. Let's see what happens here. If I hold this in front, so 9's there, down prime, right prime, down, right, down, front, down prime, front prime, and how about that? Let's move that up. And you can keep reapplying this. So now red, white goes up here, do this move again. And notice I've left alone everything up here. And now I have these here. Now, let's see if I can, yeah, so this one, same thing. Gotta go up here. Okay. But now here's one last thing. So I might ask you this. The last one I've got to replace up here. Notice that it's off, right? Because the color is going to slide up in the wrong place. How am I going to do that? Right? I mean, because if I apply this, it's going to go up and the color's going to be wrong. Well, what I can do now is just do the mirror image of this, right? So I sort of take the mirror instead of down, I now go this way. So here, I can get this slid up there. In theory, I have given you enough information to now get 2 rows. But see if you can figure out what I did there. What's the mirror image of this, right? So instead of sliding up like this, I want to slide up here. In other words, I want to run this in reverse. See if you can look at this, and instead of doing this, do this. Translate that move to its mirror image across this axis. See if you can come up with that. And if you can't, we'll talk about it. question?
What exactly do you mean by mirror image?
Well, so for example, what I wanted to do is I wanted to slide this here, but it was going to give me a wrong color. So actually what I want to do is the mirror image over here. So the first move in sliding it here is turn down counterclockwise, so fold away. So doing the mirror image here would be down the other way, right? The second move in the mirror image is right prime, so you're folding into this. So the mirror image should be front clockwise. See what I'm saying? So instead of going turning into this curve here, you turn it the opposite way. That's what, so imagine that the mirror of symmetry is right along through the diagonal of the cube one. See if you can figure out what that is. Yes.
So what process did you go through to arrive at that in the first place? Like that set of operations?
Oh, I wrote down some stuff and got the permutations to work out. So I literally did it with pencil.
So if we knew what the destination, result, like operation one before was, is there like a general process to arrive?
I'm sure that one could design some kind of algorithm to do that. I just kind of did by looking at it as algebra, so I didn't do it like a formal process. I'm not sure the answer to your question. I'm sure that you could, maybe come up with that.
Well, I mean, if one of us were to sit down and try to do what you said, like work it out on paper, we would probably come to similar results.
That's exactly right. And I solved the Rubik's Cube actually in 2 moves. But if you wanted to like take this idea and go out and make your fortune as a speed cuber, this shows you lots of ways to find little shortcuts. Other questions? Okay, well, I will see you all next time.